try to make this big enough. That might be too big. The probability of an event, how likely is to occur, and how often will happen. This is a basic formula. So the number of ways an event can happen divided by the number of possible outcomes. When you let's see right here. We have this. We have a jar of marbles right here. Three red, 2 green, 1 blue. So when you write out the probability of red, you write it out like this. It would be P red equals so if I said if you randomly select one marble what is the probability of each color? Well, red, there's 3 reds, right? So it's the number of ways something can happen over the total number of outcomes. There's 3 reds in there. There's 5 total marbles. So it's 3 over 5. Green would be, well, there's 2 greens and there's 5 marbles, so it's 2/5. Okay. Two out over 6, and then blue would be 1 out of 6, so 1 over 6. And then, what about a deck of cards? of each card. Let's take a look. Well, what if we just wanted red and black cards? It would be, well, there's 52 cards in the deck, and half of them are red, half are black. So there's 26 red cards over 52 total cards. There's 26 black over 52 total cards. And the other ones that we'll do is we'll do some of the suits, like club. Yeah, they're all going to be the same. Club, diamond, spade. There's 13 of each suit in the deck, so each of these is going to be 13 over 52. Notice how some of these would reduce, like the 26 over 52 would reduce to 1/2. This would reduce to 1/4. And if we wanted to do each of the different numbers of cards, what I'm meaning 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, they would all be 4 out of 52. Maybe we'll do the ages of 4 people. I'll have to give them some ages. 15, 17, 18, 21. If you randomly select one person, what are the probabilities? Well, let's just do 15 for the first one. These ones will be a little bit harder. This one is going to be between 17 and 18, including 17 and 18.
The overhead projector.
It's getting cut off.
Being a jerk.
Greater than 18. 18. The last one I'll do is less than 17. So 15, there's one person who fits that. It's 1 out of 4. Between 17 and 18, if we're including 17 and 18, it would be 2 out of the 4 people, which reduces to 1/2. Greater than 18 would be, well, 18 and 21. 21 is the only one that's greater than 18. None of the others are greater than 18. So it's 1 out of 4. If I had said greater than or equal to 18, it would have been 2 over 4, because that's 18 and 21. Less than 17, 15 is the only one that's less than 17. So it's 1 out of 4. And what if we can also do probabilities with something called z-scores? A value that shows the number of standard deviations between a single value and the mean. Here's a simple example. What if these are the ages of a population of 5 people? Ten. Love some younger people in here. Age. This just shows that these are the ages of the 5 people. 10, 14, 10, 12, 14, 16, and 18. We need the mean of these numbers first, because what I'm going to be doing is I'm going to be calculating the standard deviation of this group of people. So let's calculate the standard deviation. We need the mean first. Ten plus 12 plus 14 plus 16 plus 18 over 5. It actually comes out to the middle, because 22, 36, 46, 52, 70 over 5 is 14. Now let's subtract each number by 14, because that's our mean. So we just have to get this out of the way first. All we want is a standard deviation. So we're just going to square each of these. Um, two squared, 4 squared. Here we go. 16. And I'm going to show you how this relates to what we were doing earlier with probabilities, but first I just have to show you what a z-score is. This just comes from the squaring. This adds up to 40. It's a population, which means you divide it by 5. You don't drop it down to 4. And then it comes out to 8. That looks like what I got with my last example I did at the beginning of class. Then it's the square root of 8. So what we did was we squared the answers. We found the mean of the squared answers. And we found the square root. There we go. And I think this is about 2.83. Great. What we can do now is we can take this, it's our standard deviation, the square root of 8. I hit the square root key. 8 square root is 2.828. Now we can take our ages of the 5 people, and for each one, we can get z. There's this formula right here. Ten minus, well, z equals x minus the mean divided by the standard deviation. So we have to do that for each of these. The first one would be 10. Each of these values is our x, because an x is just a regular number in this case. So our first x is 10 minus the mean of 14 over the standard deviation of 2.83. We get negative 4 over 2.83. Well, 4 divided by 2.83 is 1.41, and then we make that a negative because it's a negative divided by positive. So this right here was actually negative 1.41. This is the second one, 12 minus 14 over 2.83, which will be negative 2 over 2.83. Negative 0.71. And then if our next x is 14, I'm out of room down there, so I'll continue it up here. Do you want me to say it again? What is that? I don't know where that came from. This is 0. Sorry, I missed that. These are just going to be the positive. This is going to be the positive version of the other ones, because this is going to be 16 minus 4 over 2.83, which would be just a positive 2 over 2.83, right? And it'll be 0.71. And then the last one is will be 18 minus 14, which would be a 4 on top. 4 over 2.83 would just be a positive 1.41. So numbers that are below the mean or below average get negative z-scores. Numbers above the mean get positive z-scores. If it's right at the mean, like 14, it gets a z-score of 0. And it's showing the number of standard deviations between this person's age of 10 and the mean of 14. So this person is 1.41 standard deviations below the mean of 14. This person is 1.41 standard deviations above the mean of 14. Because if you think about the age of 14, the age of 18, which is this person's age, and the mean of 14, that distance between 18 and 14 is 1.41 standard deviations in this case, meaning 1.41 standard deviations fit in that distance between the 18 and the 14 in this case. What if the standard deviation was, instead of being like 2.83, what if it was 2? What if it's just the whole number 2? Then this one, 10, you think about it, 10 and 14. How many multiples of 2 is that? It's 2 multiples of 2. So if the standard deviation was just 2, then this would be a negative 2. This would be a negative 1. This would be a 0. This would be a 1. This would be a 2. Because that's the multiples of 2. Like, like if we had 10, 12, 14, 16, and 18, if the standard deviation was just 2 and not 2.83, this is 2, right? And this is 2 also. The mean is right here, 14. This is 2. And then 16 to 18 is also 2. So in that case, 10 would be a z of negative 2, because it's 2 multiples of 2 below 14. 12 would be a negative 1, because it's 1 multiple of 2 below 14. 14 is still 0, because it is the mean. 16 is 1 multiple of 2 above 14, so it would be a plus 1. And 18 is 2 multiples of 2 above 14. But I'm saying that this is what the z-scores would be if the standard deviation was just 2 and not 2.83. Because it just shows how many standard deviations fit between the person and the mean. So what if I said, if we randomly selected one person, what is the probability of getting someone with a z-score below -1? Meaning if we randomly selected one person from these 5 people, what's the probability of getting a person with a z-score below -1? Well, how many people are below -1? Only 1 out of 5. So it would be a 1 over 5 probability. What if I said, what's the probability of getting, well, for this one, the answer would be 1/5. A z-score above 0, well, 2 out of the 5 are above 0, so it would be a 2/5. And it turns out that, well, we did this because we actually had all the z-scores. So we could find these probabilities right here. But if the data, meaning the ages that we're working with, follow a bell-shaped curve like this, you can actually get these answers straight from the table instead of having to do them this way. You can find the probability of getting a person with below a certain z-score, above a certain z-score, or between 2 z-scores, just straight from the table. But that's only if the data, in this case ages, follow the normal curve.
Does that work only when you have a perfect bell curve?
Well, it works perfectly when you have a perfect bell curve. The further from a bell curve it is, the more inactive, the more off it'll be. So if it's about bell-shaped, the probabilities from the table will be a little bit off. But before we do that, let's say, what is the probability of getting someone with a z-score between -1 and +1? Well, wouldn't it be, this is 3 out of 5? This is too low, this is below -1. This is above 1, so it's too high, so it's 3/5. if data, if the group of people follows a normal distribution, the z-scores probabilities can be found with a table. Here's an example. IQ scores have a mean of 100 and a standard deviation of 15 in the general population. That's actually true. So what is the probability of getting someone with an IQ below 90 IQ scores also follow a normal distribution, and IQ scores tend to be bell-shaped across the people in general. So first what we have to do is find each z-score first. Remember I said how it's the number minus the mean divided by standard deviation. I think I'll be able to finish these in the next 3 minutes, I think. For this one, you get both z-scores. For 105 and 95. This one comes out to negative 10 over 15, which is negative 0.67 rounded. This one is 15 over 15, which is 1. Rounded to 2 places. And then these ones come out to this one is negative 0.33 and positive 0.133. Oh, yes?
So, is it slightly below or above, or is this not in special to the station? Like it says, what the probability of being someone below?
I'll show you next time. There is a special thing you have to do.